Hey, hello there. Today I'm looking at the question 313, super ugly number. We have to write a program to find the n's ugly, super ugly number. The definition for this super ugly number is that it is a positive number, integer number, whose all prime factors are in a given set of prime numbers we have. And also that 1 is considered as the super ugly number, no matter the set of prime numbers are, or what the prime numbers are. So we are looking at the n's super ugly number that's in the increasing order. We can see that by the example. Basically, we are asking the 12's smallest super ugly number that we can generate with this set of prime numbers. 1 is always going to be the first one in the increasing order, and then all the rest, all the numbers here are basically some kind of multiply of the prime numbers we have in the set. So if we look at this actual sequence generated, it's 1, 2 directly from the set, 4, which is 2 multiplied by 2, 7 directly from the set, 8, which is 2 to the third, 13 from the set, 14 is 2 multiplied by 7, 16 is 2 to the fourth, 19 from the set, 26, 2 multiplied by 13, 28, 2 multiplied by 2 by 7, and 32, which is the 12th smallest, n's smallest super ugly number in the sequence that's being sorted in the increasing order. So obviously, if we can actually generate the sequence or write a generator that can consistently give us the next smallest number in a line, we just ask that number generator for n times, and that number is the one we want. So then the question is how we actually going to generate those numbers in sequence. Note that all the numbers here are pretty much some kind of a multiple of the numbers we have. So if we grab a number, like say 4, the multiplier between the product between this 4 and those prime numbers are going to be somewhere later in the sequence. The 2 multiplied by 2, 4 multiplied by 2, the 8 is going to be here, later in some later position in the sequence. 4 multiplied by 7, 28 is here, and 4 multiplied by 13 is even further down in the line. So what we can do is basically starting from 1 and have that number, the smallest number we currently have in the sequence, multiply that by the each individual prime numbers in the set, and put those product into a set. And after that we are done with number 1. We move that into the sequence. Then we try to grab the next smallest super ugly number from the bag of super ugly number that we generated. It's 2, so we multiply 2 by the individual prime numbers in the set, and then put all those product back into the bag of generated super ugly numbers, and then grab the next smallest. So what we can do is to use a priority queue to hold all those generated super ugly number. Each iteration we're gonna grab the next smallest to throw that into the sequence, and have the number multiplied by how many primes we have and put that back into the bag. Since it's a bag, we want to do some kind of deduplication. The priority queue does not do it naturally, so we might need to we need to create a set to do the deduplication. So this will definitely work, but it's not efficient because just think about that we actually have the bag size to be growing quite dramatically somewhere down the line. So the runtime is not going to be ideal. We will look into the code and do some analysis, and it's not going to be strict because I'm still struggling trying to figure out the exact mass. So we're going to look at some loose upper bound instead of the actual tight lower bound. So tight bound. So let's code this. It's pretty straightforward. So we're going to use a priority queue to use that to hold the set of generated super ugly number, and each iteration we grab the smallest to put that into the sequence, and then use that number to generate a new additional super ugly number and throw that back into the bag of generated numbers. So pretty much just create a really naive super ugly number generator. So we're gonna have this priority queue, which initially is this number 1 by itself, and we use a set to do some kind of deduplication. So in the beginning it's just the number 1. So we have to generate n number. So while here we're gonna grab the next smallest number from the priority queue. So it's I will be using the heap queue from Python itself. Why heap queue? I'm not misspelling, right? Heap pop pq. Because by default it's actually the min priority queue. So if it's a min priority queue, that satisfies our requirements, because we're gonna consecutively grabbing the next smallest super ugly number that we generated. So it satisfies what we need. For prime in primes, we're gonna multiply the number with the prime. That's the potentially the new number that we generated. If it's already something we have seen, that means we have already pushed this number onto priority queue already. We don't want to do this duplication. Otherwise, we will push this number onto the priority queue and also add the number into the set of numbers we generated so far. So what we would do is to push this number onto the priority queue and also add this number to the priority to the set. So after this for loop, we are done with this number. We officially move this into the sequence and decrement the number we have already generated. Here I'm not actually collecting this because all we need is the very last number being popped out from the priority queue. So after this while loop, we should just return this number. Yeah, so there's a little bit of optimization. If n is equal to 1, the number is what we want. So let's actually do that. So for that we don't need this, right? Yeah, so we don't need this return. So let's see if it works. Cool, looks good. Let's see. Yeah, it's about mediocre. Yeah, somewhere middle in the runtime among all the submissions, but it's actually quite slow if we analyze the code. We definitely have an order of n here. It's a while loop and it's decremented by 1 every iteration. We got a pop here, which is a log of the size of the priority queue. Size. Let's call this s. The size of the priority queue is growing, so it's a slightly complicated problem. The prime, the for loop here, it's potentially order of k, but it's not necessarily k multiplied by the push here, because the push is also log with respect to the size of the priority queue. But since that we're doing some kind of deduplication, it's not necessarily k, but so let's just say that in the worst case it's order of k. So the whole thing is these 3 things multiplied by together. So it's gonna be loose. So it's nk multiplied by log of size of the priority queue, and the size of the priority queue is actually some kind of function of both n and k, but it should be less than linear. So in the very worst case, it should be n multiplied by k. So that's the very loose upper bound for the runtime complexity. It's nk multiplied by log of nk. So it's actually quite bad. And if we look at what's kind of a redundancy here is that this thing grows unnecessarily. Let's say that we only want 12. We can potentially generate far more than that. So you know, it's the two multiplied by together. That could potentially be something like 48. So that's definitely far more than what we need here. So let's say, so obviously the thing that we want to do is still to follow this kind of track to generate the next smallest number using priority queue. We need to do some optimization. So here we actually create a lot of large number that's too far away down the line. So the code is easy and very lazy, but the work under the hood is quite busy. So we're actually gonna do the opposite. We're gonna try to have the work to be a little bit, the code to be a little bit more complex, but have the actual work down there to be lazy. What I mean is that I'm not gonna generate all those combinations. I'm only gonna multiply this by make this number slightly larger in the sequence and put that back into the priority queue. So let's look at this. This is the desired sequence of numbers, and the primes are here. Oh. So every number has to be sum multiplied by either 2, 7, 13, or 19. Just think about how we actually gonna do this. Initially, we only have one, so let's just put a 1 here, and we have 4 different branches to sort of. So let's see that we have a 2 here, some number multiplied by 2, and 7. And 13 and 19. So initially this sequence is only the number 1. We will multiply this by 2. That's actually the number we want to put back onto the priority queue. Then what's the next possible next number we want to put on the priority queue? The number of the sequence of super ugly number that we generated. It's going to be 2 multiplied by 2. So we actually have this kind of a next relationship. 2 is going to multiply by the next smallest in the sequence, which is going to be 4. And now 4 is the smallest. We put that back to the end of the priority queue. The number, the priority queue basically here is the generated super ugly number. And then we find a 7 here. We're looking for the next smallest, which is just going to be 7. So we'll put 7, move 7 up. And for 7, we will, the next smallest super ugly number we can generate by something multiplied by 7 is this 2 multiplied by 7. So it will be the next super ugly number that generated by some number multiplied by 7 is going to be the 2 multiplied by 7. It's going to be 14. And the next number is going to be so 7. The next number is going to be 2 multiplied by 4. So I'm just gonna promise I will do this a few more iteration to it will become super clear what we are doing here. This is 8. That's the next smallest super ugly number in the sequence, and also the third number from this sequence. This sequence here is 1 multiplied by 2, 2 multiplied by 2, 4 multiplied by 2. So after this, it will be 13. We move 13 into the sequence, and then the next number that's going to be some number multiplied by 13. Next super ugly number in this line is going to be the next one, 2 multiplied by 13, which is going to be 26. So so each individual line here is basically a sorted linked list, and it's sorted list, and it's actually growing dynamically while this sequence of super ugly number is growing. It's growing as when at the same time this list is growing. So all we need to do every time is actually just do a priority queue. Is checking the 4 head node inside among these 4 lists. So all we need to do is to keep a priority queue of size k. So that's much better than this here, because we see that n multiplied by k is actually fine. The thing that's really bad is this log nk. That's a multiple of that. If this becomes much smaller, then the whole thing is smaller, because n is definitely has to be there. K, the n multiplied by k term is definitely going to be there. The latter multiplier should be as small as possible, and this latter term is tied up to the size of the priority queue. Looking at here, we can basically this is like merge 4 k different sorted list, and the next element we grab, next head node we grab from this 4 sorted list that's advancing dynamically as the sequence, the actual sequence grows, is to use a priority queue to keep track of the 4 head node here. So let's think about what this head node actually should contain, the information that this head node should contain. It will be, let's see, it's a two-dimensional thing, right? The actual number here, it should be a 3-dimensional thing. The actual number here, the column it belongs to, this is the first column, this is the second column, this is the third column, and the multiply, the prime multiply it has. So it will be the number, which is like 8 here, the index, the column, which is going to be 3, and the prime multiplier, so that is 2. So every single number here, every single node inside this k sorted list is triplets of 3 things, and we're just gonna put this thing, the 4 of this thing, k of this thing, on the priority queue. Each iteration we're gonna pull the smallest node in terms of the first element out, and use the second item, the second value, the column, increment that by 1 to grab the next value in the line, and multiply by the prime it comes with to put that back in there. So so as an example, what we currently have is 8, 14, 26, and 19. So the next smallest is going to be this. What we need to do is to increment this column number 3 to 4. So we'll grab 7 and multiply 2 by 7 to get the next element here, next node here, which is going to be, why it's not shrinking. It's going to be 2 multiplied by the 4s from the sequence. It's going to be 14. Yeah, so we're basically updating this node from this to this. Yeah, so this is the update, and we pop this out, modify the second column, multiply this two. Look up at the number from the using this column number from the actual sequence. Multiply the latter to get to the update the number and push this back to the priority queue. So that would be a better solution. The size of the priority queue is always going to be 4. So this kind of query will be log of k. So much better than this. It's not growing with respect to n anymore. It's fixed with k. So it's much better. So let's code this up. Oh, sorry. It's not meant to happen. So we're gonna have the sequence of number that's generated so far. It's going to be a growing kind of array or linked list, and we have this triplets as the elements on the priority queue. So let's just call this the aggregate number we generated, which is initially going to be this only number 1, and we have a priority queue, which going to be the k different initial nodes on the for each of those sorted lists, which is going to be the prime number itself and colon 0, which is 1, and the prime itself. So it's PIP. P0P, where I is 1 in the beginning. And then we're just going to do the similar thing, decrement this n. Each time we will put a new ugly number onto the priority queue, the generated sequence of super ugly numbers. And since we already have 1 here, we can run this only n-1 times. And actually here is the same thing, right? We could do this n-1 so that we don't need to do this test. But anyway, that code is already there. I'm not going to do some kind of modification to that. We're going to grab the number from the smallest number from the priority queue, which is this. Sorry. No, sorry, I think I'm forgetting something. Yes, the thing that here is we can have duplicates. Do we do anything about that? Not necessary, because if no matter which one we grab, it's just gonna advance that one more. So the size of the priority queue never really change. Yeah, so we don't need to worry about that. But that messed up the updates for this, because for 14, if it's already there in the list, we don't want to decrement this n, right? Yeah, so we're gonna grouping the node of the same value extraction into the same loop under the same iteration in the while loop. So for that reason, we're gonna first get the smallest number in the sequence, and then just grab all of those nodes with the smallest number in there. So yeah, it's going to be a nested loop. We get the top element, and the first item in the triplets is going to be the ugly number. So we try to pull the nodes from the priority queue until that the smallest is not equal to this number. We grab the triplets. This time we actually pop out the triplets. And then we want to increment the second item to indicating we are now grabbing the the next element from the sorted sequence of ugly numbers and multiply that by the prime factor and use that to update the first the actual number. That gives us the next number in the sorted list for that prime factor. And after this, we push this tuple back into the priority queue. That's equivalent to say we transferred from this to the next node in the sorted list and put that back into the priority queue. So at any given time, we're only gonna have k different items on the priority queue. So that's that, and after this while loop, we will be decrement this n, and in the end, we're just gonna return the very last ugly number we generated. Yeah, so let's give this a try. Nope, I got an error. What's the problem? Oh, when I pull this number, I should put it back to the ugly number. Otherwise, the index accessor will be out of bound. So why I'm forgetting this? No more. Oh, okay. The tricky part is that the priority queue in Python, it's the container, the underlying container, and the data structure is actually it's actually separated. I always forgot about this, so I should put this tuple onto the container. All right. No, still no. Jeez. Less than is not supported between instant list and integer. Oh, the wrong order. Ah, so bad today. This time it works. Okay. Yeah, this is much faster. Let's look at the runtime. I'm gonna do some really loose analysis. This is the order of n, and we can potentially pop k. That's in the worst case, the number is 2 multiplied by 7 by 13 by 19. That every linked list here, sorted list, that the node that we are looking at will be exactly having that number. So if that's the next number in the sequence, that's the only time this while loop will run out of k times. And each heap operation is going to be order of exactly log k, because the size of the priority queue is always going to be k. So this this second solution, the runtime is going to be loosely bounded by upper bounded by get rid of the n here. Yeah, so that's pretty much what I want to talk about this question. Yeah. Okay. Yeah, that's it for today.